wouldn't have. It didn't have very important. Okay, so why don't we proceed? So we have a really exciting new research project taking place in the physics department led by Professor Mike Mulhearn, and it's all about how to search for cosmic ray particles, and these are the same particles that we study at the LHC using your smartphone. So take it away, Mike.
Great. Hi. So I'll be talking to you today about discovering ultra-high energy cosmic rays with your smartphone. But I wanted to start with sort of my perspective on ways we make scientific progress. That's what we do as scientists. And I thought a great example is Emmy Nether, who had probably one of the most important abstract ideas of all time, I would say. And that abstract idea came from thinking about symmetries. And so an example would be if you imagine a really large pool table, right? And the situation doesn't really change much if we move that ball around. That's what we as physicists call translation invariance. And what Nether realized was that whenever you have a symmetry like that, something is conserved. Now in this example, what's conserved is the momentum of the ball. The ball heads off in the same direction and never changes unless you do something to it. Now if something breaks that symmetry, like the pool table has edges and now we can't translate the ball wherever we want, then there's no longer a conserved quantity, the direction will change. So it sounds like a simple idea, but what Nether realizes is that this is generally true. All symmetries lead to conserved quantities. It's incredibly powerful. It's actually a cornerstone of how we do modern physics. It's why we're obsessed with symmetries, why you're looking for supersymmetry, for instance. The Nobel Prize Committee is not capable of abstract thought. So they didn't award Nether a prize, as many mathematicians are wrong. But her work is so important, I'll give her 10, because I can easily find 10 Nobel Prizes that I would prefer Nether's work to. But I don't want to give you the idea that only theorists use abstract ideas. Experimentalists do as well, and Michelson is a great example. In his time, we had come to understand that light was an electromagnetic wave. It was little fluctuations in the electric and magnetic fields. Physicists looked around, and we have lots of examples of waves. We realized that waves are generally disturbances in some medium. So they asked themselves, what's the medium that electromagnetic waves propagate through? They were forced to conclude that there must be some medium that permeates all of space. Light travels between stars and the Earth, and so there has to be something there. They believe that there must be this ether. Now, this is a very abstract idea. It was understood that we weren't really going to be able to experience this except through light. But Michelson was very drawn into this, and he actually developed the technology he needed in order to try try to detect the effect of this mysterious ether, and he really actually showed that it doesn't exist. I mean, maybe it took a bit more convincing, but most people consider his experiments as the turning point that showed that it didn't exist. And that ended up being crucial. If it weren't for his experiments proving that it didn't exist, we probably wouldn't have Einstein's theory of relativity today. So an incredibly important null result for which Michelson got the Nobel Prize. So those are people that are driven by abstract ideas, but there are also people that are driven by technology. And so that, my example, is Carnot. And he looked around at the technology of his day. It was the Industrial Revolution, and so there were lots of steam engines around. And what he worked out was a theoretical model for a steam engine that it just takes energy from a hot reservoir, that's the coal, say, that you're using, and you convert a fraction of that to work, and then some of it is exhaust. And he worked out a very simplified model that allowed him and us to understand the efficiency of these engines. He was driven by these very, very practical concerns. But what fell out of this is our beautiful understanding today of processes that are irreversible. It's what we call entropy. So it's how we understand today how you can have irreversible processes like a glass breaking. You never see that happening in reverse. A glass never reassembles itself, right? But the laws of physics that underlie holding the glass together could run backwards. So there's something strange going on, and it was really this very practical concern about steam engines that led us to our modern understanding of this. So Carnot, his work wasn't actually appreciated in his lifetime, so he also didn't receive a Nobel Prize, but he did have a French pension, which is honestly just as good. So that's Carnot. Last historical figure I want to mention is Einstein, and we're actually going to need to use a few of his results. So here he is visiting Davis Farmers Market, where he allegedly had his great idea that he equals mc squared, right? This is the idea that we can convert energy and mass, and we can convert mass to energy and energy to mass. Very important idea to us in what we do. Now, Einstein was a theorist, but he did do one experiment, and he's Einstein, so he won the Nobel Prize for it. And what he did in this experiment was demonstrate a new process that what we're doing today relies on, and that's called the photoelectric effect. Now, this process just allows incoming light particles to affect a metal that they're incident on and actually produce electrons. So it's a way to have a light particle, a photon coming in, and actually produce an electron. And that's how your smartphone cameras work today. So why all this introduction? I think what I'm trying to point out is that science connects ideas with technology, right? But we shouldn't think it's a one-way street, right? This really happens in both directions. It's a connection, and sometimes the technology drives the ideas, and sometimes the ideas drive the technology. So we really want to approach it from both ends. So how do I approach it? Well, I would say I work on the CMS experiment with all my other colleagues on the UC Davis faculty here. And we're really driven by the really exciting abstract ideas of our time. So Max talked about quite a few of them, but there's other ideas. We want to know about dark matter. We want to know why some fundamental particles are so heavy. All of these interesting questions. Now, in order to answer these questions, we have to build these really marvelous, these just beautiful, almost miraculous machines, just feats of technology in order to answer these questions. And that's really quite a lot of fun. Now, I'm not going to talk a lot about CMS. Max already did, and I gave a talk about the Higgs here at Picnic Day in 2012. I did just want to show you one plot from this. So this is 2012 before the Higgs was discovered, and I gave a little example where what our data might look like with the Higgs at about 125 times the mass of the proton. You can see I'd like to give out a Nobel Prize. I gave us the Nobel Prize for if I were on the Nobel Committee, everyone would have a Nobel Prize. So I just want to show you remind you what Matt showed us. So here's what we actually discovered was a Higgs boson at about 125 times the mass of the proton. So if you were here in the 2012 Picnic Day, you saw the Higgs discovery before it was discovered. And also, of course, the Nobel Prize prediction did come through as well. So this is great fun, the CMS experiment. Great colleagues here at UC Davis. We have a lot of fun doing what we're doing. But it's the 6 of us and, well, about 3,000 of our closest friends. And, you know, we're physicists, you know, there's a lot of stereotypes about us, and they're all true. You know, we're putting that many physicists together, you know, it's fun, but it can be straining in some way as well. And so, really, I've been talking about this with my good friend Daniel at UC Irvine for many years, and we've always been looking for sort of a side project, and CMS is clearly what drives us. But we wanted to find, we've been asking ourselves, you know, is there some sort of experiment we can do on a smaller scale that we can control ourselves? And to attack it, we were really asking, you know, what's the exciting new technology of our time, like Carnot and the steam engines, you know? Is there something like that we can leverage, and can we apply it to some unsolved problems? And, you know, after many discussions, it really just kind of, you know, it's obviously that what we should be doing is do something with smartphones. So we really have been driven by the technology in this case. And then we went looking, you know, it's like we had a camera and we went looking around for nails, right? Which is a totally valid way to approach science. And so what we found is that we think they're useful for understanding these cosmic rays. So what cosmic rays are these very high energy particles that are that come from outer space. We'll talk more about that. And they collide with atoms in the upper atmosphere and produce lots more particles, which go off and collide with other atoms and produce additional particles. And so you get what we call a shower of lots and lots of particles as a result of it. Now, we understand where a lot of these cosmic rays are coming from. They're coming from things like solar activity that's very close by. They also come from the shock waves that when you have these tremendously violent supernova, there are shock waves that can actually accelerate charged particles to very high energies, and then eventually they reach us here at Earth. So we understand a lot of these sources, and so we can sort of look at these incoming cosmic rays as a function of energy. So remember, E equals mc squared, so the units of energy I'm using here are you know, one mass of the proton. Okay, it's just a very convenient unit of energy for us. You know, kilowatt hours are not useful for us. And then what I'm plotting here is how often we see these events. So these are the lower energy things, and these are getting to very, very high energy, about 10 to the 15 times the mass of the proton. So, and what we see are these low energy events happen about, what this is saying is that if we have a little meter squared target, then we would really have an event of that energy about once per second. Okay. If we get down here, they're getting rarer, so that same meter squared target, you have to wait a year to see an event with that much energy. And when we get down here at the very highest energy, you need a whole kilometer squared target, and you have to wait a whole year on average to see a single event. So we're getting to very, very rare events here. And now what it turns out is that, you know, these more common events, we have a pretty good understanding of where those are coming from. But these very, very high energy, very rare events are not very well understood yet. And so that's what we want to attack. And so, you know, there's lots of ideas of where these could come from. This is the most far-fetched explanation, right? So alien civilizations making cosmic accelerators. So I don't know if you guys know this rule, but whenever an article, the title is a question, the answer is always no. So you can affirm that rule. But you know, we are asking ourselves these sort of questions and trying to understand it. And this very intriguing result from the incredibly boringly named telescope array. What a way to name a project. They have a 19 event excess that they see of these very high energy particles coming from one particular region in the universe. So that's extremely interesting, but it's really hard to nail this down further because these are just such rare processes. So we're thinking of getting into this game, and so we look, of course, how the professionals do it. So there's the Pierre Auger Observatory, and what they're looking for the same things as us, these cosmic rays of varying energies, and so the cosmic rays produce these showers. And so what happens actually is when these particles move through the atmosphere that has nitrogen in it, the nitrogen gives off a little bit of light, of fluorescence, and so they have very sensitive detectors that they point towards the sky that can actually see that bit of light. And they also have gigantic tanks of water, and what happens is when these particles that are traveling very close to the speed of light in the vacuum hit that water, they're actually traveling faster than the speed of light in water. And so they get essentially what the light equivalent of a sonic boom. So we see a flash of light that's called Cherenkov radiation. And so this is a great way to do it. This is really how you want to do this experiment. But on the other hand, you have to build the experiment, right? And this is an enormous scale. So this Auger Observatory is 3,000 square kilometers. That's about the size of my entire home state of Rhode Island. So it's hard to imagine scaling up this experiment for the small ones, but absolutely. Yeah, right. Right. So that's about the only thing we have going on them, right? That's about the biggest scale you can imagine building, unless you compare it to the smartphone network, right? So they're just located in this tiny part. So if one of these very rare events happens here or here or here, they're not going to see it just because they don't have a detector there. Okay. So what's an ideal detector? Well, it'd be great if we covered the entire planet, right? It'd be great if someone else paid for the detectors for us. That's always good. We need the devices to be remotely programmable, and detectors require shifters, so we need a dedicated shifter that's taking care of our apparatus. And that's exactly what the smartphone network does for us. Our volunteers are going to be our shifters that run our application, and they're just going to donate time on their smartphones while they're sleeping. So how does this idea work? Well, what we're doing is he's taking over the smartphone camera, and we actually use the video feed from the smartphone cameras. And the way these smartphones work is based on photoelectric effect. So essentially, the visible light, can come into these silicon devices, and by that photoelectric effect that Einstein discovered, they actually produce electrons, and we can collect those electrons and measure the number of electrons, and that tells us about how much light is there. We put it all together, and that lets us reconstruct a model for what the picture should look like. So that's how the phone works. Now, from our point of view, this looks exactly like the silicon detectors that we use in our experiments. In fact, I think Max even said this is like a gigantic digital camera. So they're very similar, very related technologies, and so we can use that. So that was just an idea, right? And so early on, we had to test if this idea would really work. And so what we did was we took some radioactive sources that were what we call gamma emitters. So they produce high energy light particles. And we just placed those near a phone that was running our very rudimentary at the time application, our sort of first pass app. And then we just looked at the data. We looked at the energy that those pixels from the smartphone camera, essentially how bright a pixel in the photo was, and we compared. So this black is what we got when we had no source present, and we immediately saw that when we started adding sources, we had quite a different shape actually, and quite larger pixel response. So this was our first hint that our idea might actually work. It was kind of a surprise to us. Most of our ideas don't work.